Good afternoon. Thank you for coming. I know it's always hard to compete with good food, so thank you, everyone. Are virtual threads going to make reactive programming irrelevant? Well, if you're really hungry or if you miss coffee, I can answer right now, yes. So if you want to have some food, or if you want to stay to get the longer answer, then you can stay a little longer. So it's all about concurrent programming, virtual threads, structured concurrency, all these kind of good things, and reactive programming. Because Loom is a project that required a massive effort from the engineering point of view. And also a lot of investment, a lot of money was put into that. So I would like to really show you, go back to the beginning of the problem, go back to the roots, okay? Explain really what problems Looms wanted to fix in the first place and how it fixed them so that you can make an educated guess. Should we use virtual thread and structured concurrency, or should we carry on using reactive programming? So my name is Jose. Here is a set of links with some random stuff I published on the internet. I got a fair amount of content on my GitHub account about Loom and other things. But if you're really interested in that, you may check it to get some labs and examples and demos and everything about all this. I also contribute to the dev.java website, which is a great one-stop stuff if you want to learn about Java and everything. We have a playground, something we call a playground, where you can try interactively from your browser most of the Java new features that have been developed and published in the last version. And if you like videos, you can also connect to our YouTube channel, where in the Java Developer Advocate team, we publish a lot of content, including on Loom and other things. The OpenJDK is the website where everything is happening. The Loom project is an OpenJDK project that was sponsored by some people at the OpenJDK. And you can also go there to download early access versions of the JDK. You have a Loom one. You have the 23, which is going to be released as a final version in 10 days about. You already have early access of 24 with some fixes that will make it in 23, but later. And if you're also following the Valhalla project, which is really interesting, I really encourage you to check the early access version of the Valhalla JDK that has been published a few weeks ago. That was in the end of July. All right, so we are going to concentrate on Loom. The first preview of Loom, we had it in the JDK 19. That was 2 years ago. And you can see that it was really a big effort. 100,000 lines of code in the JDK were impacted by the pull request, the Loom pull request. Everybody knows what a pull request is? Yeah? Everybody knows what a code review is? Okay. And in the JDK 21 that was released about a year ago, Virtual Thread made it as a final feature. Maybe some of you are already using the JDK 21? Yeah, that's a fair amount of you, about 30%, I would say. And probably maybe some of you already experimented with virtual threads? Oh, that's almost the same amount of people, so that's great. That's great to hear. So virtual threads have been integrated. It doesn't mean that they do not continue to evolve. They do. There are optimizations that are currently being made at the JVM level, so it's completely transparent. And if you moved from one version to the other, you will benefit from these optimizations. There are several things, memory-wise, that we're going to talk about more, and also things like pinning that are going to be, some of the pinning issues are going to be fixed. Some are not going to be fixed because you can't fix them, actually. Structured concurrency, which is the second part of the Loom project, is still a work in progress. It's still a preview feature as of the JDK 23 that is going to be released very soon. And so you can play with it. There's no difference between 22 and 23 for structured concurrency. And the people are saying that they are just expecting some more feedback from the people who are playing with that. So if you have any feedback on structured concurrency, if you need features, if you have use cases, precise use cases that you think it could be worth to make them as part of the API, by all means, publish that on a mailing list, talk about it, make some noise, because it could have an impact on the way structured concurrency makes it as a final feature in a JDK. And it's the same for scope values. Scope values are also a preview feature that will make it as a final feature in the future. Scope values are a model meant to be a replacement of thread local variables. And we're going to talk more about that at the end of this presentation. Anything you can do, you want to do, the official URL you need to connect to is this one. Okay, jdkjava.net/loom. This is the entry point with all the mailing lists, all the documentation, all the wikis, the early access version, and everything. That's your one-stop stuff about Loom. What's amazing is that as soon as VirtualThread were published as a preview feature, all the community, all the great frameworks you can think about really, I wouldn't say embrace, but works with VirtualThreads and propose solutions to embrace VirtualThreads. Okay, and probably the most prominent of them is Elidon Nima, which is the version 4 of the Elidon framework, which is an application server framework. It's entirely based on VirtualThread. All the core kernel of Elidon was rewritten to support VirtualThreads and to get a new performances and new patterns of code. What does it mean to be irrelevant? Okay, because of course it's a kind of a baity question. Is it going to make something we've been using for 10 years irrelevant? Okay. It turns out that VirtualThreads and reactive programming are about to solve the same problem. And reactive programming has been solving it for more than 10 years. Okay. If you're in this kind of business, you've been using reactive programming for a long time, you already know these techniques and these technologies very well. There are several frameworks that are doing that. They are doing wonders. We know exactly how it works, and we know exactly what you can expect from them. So that's not the point. It turns out that VirtualThreads are there, but structured concurrency is not there yet. So is it solving the problem now? I would say partly, but not entirely. And we'll probably talk more about that when we have structured concurrency as a final feature. So far, it looks promising. You can play with it. You can experiment with it. You can have a look at what it will bring in the future, but it's not completely there yet. It's all about fixing concurrency issues. Now, if there's a tough problem in programming, it's probably concurrent programming. Okay, and we are only talking about a certain type of concurrent programming, which is how to improve the throughput of your application. We are not talking about doing some kind of in-memory computations, like with parallel streams, for instance. We are really talking about throughput, right? And currently, the right paradigm, the right programming model to achieve the highest throughput possible is to use callback-based reactive programming. And we are going to talk more about that. Why do we need that? Well, we're going to take an example, a very simple one, actually. You need to query some kind of server. Maybe it's a page that you are analyzing, whatever. ReadImage is going to make a query on the internet, and ReadLinks is also doing the same. You get a result, and from that result, you build a page with these two elements. So, quite simple example. That's the kind of pattern you would have write probably 20 plus years ago, because everything was so slow so that having a 300 milliseconds response time was okay. That was the internet was working at that speed. Well, speed, slowness, I don't know how to call that, but that was okay. Nowadays, you don't want to write this kind of code anymore. Why? Because the first request is going to take about 100 milliseconds. The second one is probably going to take the same amount of time. And during this time, your CPU is doing nothing. So you want to try to do these two requests at the same time in parallel, so in two different threads. So you need to go multi-threaded. Well, it turns out that in 2004, we have a nifty solution based on the executor service pattern. That's the Java util concurrent API that is bringing this kind of pattern. And you can write your code in that way. Now, it's not exactly a 2004 pattern because you have lambdas and the var keywords and this kind of stuff, but it's just syntactic sugar over a pattern that has been done 20 years ago. You have an executor service that is a pool of threads, okay, and you submit a callable to this pool of threads. You get a future. You do that for the images and for the links. And now the nice thing is that the two requests are going to be conducted in parallel. So instead of waiting for 100 plus 100 milliseconds, you now wait for 100 milliseconds at the same time. So you're saving about twice the amount of time. And then from that, you create your page. And that's probably that was a good pattern 20 years ago, but it has actually a number of bugs in it. There are obvious bugs, and I would say less obvious bugs. Okay? What's wrong with this code? Well, the first thing that is wrong is that it blocks threads. And blocking threads is bad. Okay? Why is it bad? Yeah, nobody knows. I agree with that. So we are going to talk more about that also. How many threads does it block? Well, it depends really on the amount of threads you have in your executor service. But if you have more than one, then it blocks 3 threads. Okay? The first one is a thread from your, well, the first 2 are threads from your executor service. And the third one is your main thread, the thread that is running this code, right? Because the get call are also blocking calls. So this is really bad. This is really bad. Blocking a platform thread is wrong for many reasons, and here it is blocked for about 100 milliseconds, which is the speed, well, the time it takes to make a network request, if your network is not too slow, of course. But it's not the only issue. That's the obvious issue, I would say. There's another issue, which is a sneaky one, is that it can lead to a loose thread. Okay? If you take a look at this line, and suppose that there's something wrong in this get, that the get crashes, throws an exception at some point, and it turns out that at the same time, there is something wrong going on in read links. All right? Like the server that is giving you the links doesn't provide any answer. Well, you wrote your code the best you could with the timeout on the get method, but it turns out that the second get is never called because the first one threw an exception. And because the first one threw this exception, the second one is not called. So in your executor service, you may end up with a thread that is going to be freed, to never be freed, to be kept busy forever. So you spend a lot of time fine-tuning your application very precisely, okay? 16 thread is really the best that we can have in this executor service. And after 3 days, you realize that your application is not working that well. It's like you only have 15 threads working in this executor service. Okay. And you wait for another 2 days, and then from 15 you went to 14, and then to 13, and you end up with only 9 threads working, which is about half of what you were expecting. So what do? Well, you restart your application because you have absolutely no way to understand what these threads are doing. They are just blocked forever. Okay? So you restart your application, and after 3 more days, guess what? It starts again. Okay? Well, good luck trying to fix this kind of bug, because there's really nothing you can do but check your application and see that, yeah, there is this kind of bug in that. So having loose threads is really annoying, and it needs to be fixed at some point. And we're going to see how Loom is proposing you a response to that. The third one is that it's hard to debug, and it has to do with stack traces. And I'm going to show you examples of stack traces when you're using this kind of code. Okay, we are going to talk more about that in a minute. And the fourth reason is that it's a stupid code. Everybody agrees on that? Yeah. Okay, so I can move on. It's stupid because if you're doing reactive programming, you're just declaring everything, and your reactive framework is taking care of the rest. Okay, and you free your main thread, which is probably some kind of thread that is doing some HTTP request, and you don't take care of anything. And this thread is just doing nothing but declaring everything that has to be done. Okay. So we have 3 things to fix. Stupidness is very hard to fix. You can't really fix that, so that makes 3. First, the blocking of the threads. Second, you want to have relevant stack traces to be able to debug your code. And third, you don't want to have loose threads anymore. You want to shut down this possibility in your application. All right. So what is a platform thread? Because Loom is about providing a new model of thread, which is called a virtual thread. And virtual threads are defined I wouldn't say against, but it's another model of thread compared to platform thread. Platform threads are expensive, but it's not on the Java part. Java has nothing to do with that because the Java long thread is just a wrapper on what is called a kernel thread that is provided by your operating system, or a platform thread, which is the same. And a platform thread takes about 1 millisecond to start, which is a lot. It was not a lot 30 years ago, but nowadays it's a lot. And it allocates 2 megabytes of memory to store the stack of that thread, because the threads like to have their stack in a contiguous zone of the memory. So they tend to allocate a fair amount of memory to make sure that they'll be able to avoid reallocation of this piece of memory in the future. And what is called context switching, which is the action of removing a thread from the core of your CPU because it's doing nothing and the core of your CPU likes to be doing something, takes about 100 microseconds, which is also a lot. So that's the reason why you are creating executor services in your application. You create an executor service, you launch your thread when your application starts, and then you play with them, you use them for all the lifespan of your application, right? It's because it's an expensive resource. And there's nothing much you can do about that. And if you check your operating system, it turns out that you can only have something like a few thousands of platform threads alive at a given time. There's a limit on some servers, which is between 4,000 and 5,000. Okay, so this number is actually quite low. What is wrong why is it wrong to block a platform thread? Well, back in the days, maybe some of you remember the old days of the first version of the Java EE platform. Yeah, some of them were Java EE, J2EE engineers. Yeah, okay. How to tell your age without telling your age. And the model was one thread should handle one request. You remember that? And that was great. That was a great, simple model. And by the way, that was also a model that would allow you to have thread local variables. Thread local variables are coming from that idea, which is long gone. But if you do that and you have only 4,000 threads available in your operating system, it means that you can only handle 4,000 concurrent requests at a given time, because that's the limit that your operating system is putting on you. Excuse me. On the other hand, if you consider that handling a request without counting the time it takes to wait for the response to come from the network takes probably in the order of the microsecond. Okay, on a 1 gigahertz CPU, you can do 1 billion operations per second. So if you consider that maybe with 1,000 operations, you're done with the handling of your request, it means that it's probably 1 microsecond. And you have a factor of 1,000 between the number of requests that your CPU can handle, can manage, and the number of requests that your operating system gives you if you keep this model 1 request per thread. All right? You are losing a factor of 1,000. You have a CPU that could be handling 1 million requests per second, but this stupid model limits you to 4,000 requests per second. And you want to do better than that, of course. And this is exactly what reactive programming is doing. The programming model where you have 1 request per thread is not working anymore. You cannot work with it. Okay? And it has been the case for more than 10 years now. So what solutions do you have? Actually, you have 2. Okay? And the first one is reactive programming. What is reactive programming telling you is that instead of having 1 process to handle your requests and to provide a response, you are going to split this process into small lambdas. Each lambda should not be blocking. It's forbidden to write blocking code in the lambda expression. It's such a lambda. Okay? And you are going to feed these lambdas to a reactive framework that is going to wire everything together. That is to take the output of the lambda and make it the input of the next lambda. All right? How many each platform thread should be able to, how many lambdas, sorry, each platform thread should be able to handle? Well, at least 1,000. If you have 1,000 threads and each thread can handle 1,000 lambdas, it means that you'll be able to handle about 1 million requests. And that's the limit your CPU is putting on you. You cannot go past this limit. Okay? So it means that you take this code, you write it with a reactive framework. So I chose the completable future API because it's an API from the JDK, but it's not the only one. Okay, and it gives you this code. You see the read image is the first lambda that you have. Supply async read image. When complete is actually your try catch. It's handling your exception. In a when complete method, it takes a big consumer, and the first consumer is the response that can be null, and the second parameter is the error that can be null. Either one of them is null. If an exception was thrown, then error will not be null, and there won't be any image. And if there was no exception, it will be the contrary. So you need to handle. This is how you can handle this error. Okay, so you basically have two lambdas, and you do the same for the links. So you have a second completable future. And then you need to wire these two completable futures together, telling when the two results are available, then I want to do this. And this is the run after both. That's the run after both method. Okay, it's a method on the first completable future, takes the second completable future as the first argument, and then do something with both. So here on this code, cf1.get and cf2.get are not blocking code, because cf1 and cf2 are done. They provided the response, they carry the response. Okay? And you can see that, I'm going to show the previous slide once again. This code is fairly simple to understand, right? This one, it's not as easy to understand. And this is a very simple example. I mean, it's hard to come with a simpler example than that. And that's the first price you have to pay when you embrace reactive programming. The price to pay is that you write some code that is hard to write, hard to read, and thus hard to maintain in the long run. If you want to modify this code, then you first need to understand what it's doing, and it's not always easy to do. And that's only the first price to pay. We're going to see more than that. But if your reactive framework is working properly, and if you didn't write any bug, that is, none of your lambdas is doing blocking call. Okay, read image is not doing a blocking call because it's just issuing the request, and then your reactive framework will realize that the response will arrive in a certain amount of time. So after this amount of time, it actually registered on some operating system signal that will say, hey, the data is available. And then when the data is available, it will call the lambda of the when complete method with the data. So if we check, what I would like to take a look at is the thread that is going to execute all your lambda, and to analyze how it's kept busy by the completable future API. Okay? So first, that's the request on the images. All right? So you launch this request, and the response will arrive sometimes in the future. The response arrives later, and that's the processing of the response. It's probably some JSON object that you're going to marshal to create Java objects. Okay? And then when you are doing the same with the links and everything is okay, you are going to process the result images plus link at some point in the future. When is this going to happen exactly? You don't know. But the completable future API that registers on these operating system signals knows when the data is available. So it's the job of your reactive framework to arrange everything on this timeline. Okay? But in the meantime, you can launch another request. For example, for the links. You launch the request, at some point the response will arrive, and then what you can do with the image and the links is produce the page. And that's the last task that you saw. Okay? But because you have so many requests on your server, well, you can handle another request on some more images. That will produce a result at some point. Oh, it turns out that there was just this slot at this time, so yeah, let's carry on with it, and then produce a result. Okay? And you are going to do that again and again, some more links that will be processed later when they arrive, and then some more images, and then some more links, and some more images, etc. So if your reactive framework is doing its job, it will keep your platform thread busy 100% of the time. And this is what reactive frameworks have been doing for 10 years. Reactive frameworks are very good at that. Okay, so it's not because you are going to move to virtual threads that you are going to gain amazing performance, because your platform threads are already 100% busy. All right. One thing that you should absolutely avoid is writing some blocking code in your Lambda. You see that if one Lambda is blocking for like 100 milliseconds, each of these Lambda is 1 microsecond. Okay. So if one of these Lambda is blocking for 100 milliseconds, then not only it will kill the performance of that request cycle response, but it will also kill the performance of all your application. Because a given platform thread is actually handling so many request response cycles from many clients and from many services, that it will really block everything. And that's a bug, and you need to fix it. And good luck fixing it, because it's not that easy to do. Don't have many tools to do that. And now suppose that something goes wrong when you're calling read image. Okay, so you just write this code, and you see you have a line number here, which is line 27. And read images is it's throwing an exception. The stack trace you get when you have a simple line of code like that is just, okay, in my application on line 27, I have this exception that has been thrown when I called read images on the some service class on line 12. Okay, and this is a very nice stack trace, because I can see exactly where I need to debug my stuff, or where I need to put a breakpoint. Now, if I have this pattern of code with the executor service, and I do the same, so I create an exception in read images, what stack trace do I have? Well, I don't have the exact same stack trace, because the main thread is only calling submit, which is not a blocking call in itself, okay? And it's another thread that is going to execute read images. All right? But I will see this exception in my main thread when I call get. And this exception will be wrapped in some kind of exception generated by my future object, okay? F1 is a future object. So the exception, the stack trace is now this one. You see that I have a first stack trace that takes me to the line 32, which is where I called get, because this is where the exception is thrown in my main thread. Okay, and that's the execution exception. So that is the exception that is wrapping the real exception that happened in read images. And if I check the cause of this exception, now I unwrap this exception to see the real exception that happened. Well, it takes me to some service line 12, but after that, I'm in a future implementation, right? I'm not in my code anymore. So this stack trace does not take me where I would like it to take me, which is on line 29. And now what do you need to do? Well, you have a nifty feature in your IDE called find, which will tell you read images is called in these 122 places in your application, one of them through the exception. Which one? You don't know. And if you put a breakpoint in read image, the stack trace you will have is this one. It's not going to take you where your Lambda was written. Good luck debugging that. Okay? But things can even be worse than that. So this situation is not a situation in which you want to be, right? But the good news is that this is not the pattern you're using. The pattern you're using is this one. Okay? So now in when complete, I just added print stack trace and get cause print stack trace. I don't know if you can see that. So now I can take a look at the stack trace I have if something goes wrong in read image. So the first stack trace is this one. I'm in a completable future API. I'm not even in read image. The only thing I have is the message. So zero information. But fortunately, I can call get cause print stack trace, and now the stack trace is this one. Okay? In the previous pattern with the executor service, I could go to the get stuff. Okay, if I take you back a few slides, okay, you see the my app line 32 was where I was calling get, because I was calling get. And this is where the exception would take me. So hopefully it's not too far away from the submitting of the callback. Could be, but if it's not too far away, that's okay. But in a completable future API, I don't have anything. right? And in your reactive framework is the same. You just know that something went wrong in read images. And you have no clue who called this method. Absolutely no clue. And that's one of the issues Loom wants to fix, because this is about debuggability, right? And well, only people who write bug needs to debug, so we don't need to debug. But in case you write bugs, who never wrote any bug? Okay, thank you. So asynchronous programming is efficient, no doubt about that. There's a warning because the programming model is hard to read, hard to write, and hard to test. I didn't talk about that, but it's also the case. All right. The real problem is that it's impossible to debug, and for the same reason, because the stack traces that you have are not the stack traces of your application, you cannot profile it neither. If you have performance issues in your application and you try to profile it, what you're profiling is actually your reactive framework. It's not your application. So let us go back to the beginning. I told you that there were two solutions. The first one is the reactive programming solution that has been working for 10 years, once again. All right. But there's another solution. The first problem is that you can have only 4,000 threads in your operating system, on your machine. Several thousand threads in your machine. Well, if you can build a modular thread that is actually lighter than the platform thread, and that gives you the same service, then you could be able to go back to this model, one request, one lighter thread. Okay? How much lighter should it be? Well, 1,000 times lighter. So you have an API that is working in a certain way. Your goal is to gain a factor 1,000 in performance, which is a lot. Okay? Thus the effort on the Loom project. Which is the case. You can literally have millions of virtual threads in your machine. There's no problem in doing that. Where you can have 1,000 operating system threads, that is platform threads, you can have literally millions of virtual threads. That's easily achievable, even on a small machine as this laptop. If you 1,000 times lighter is actually the minimum. It's not the maximum. If you build a modular thread that is only 500 times lighter, it means that your CPU will still be used 50% of the time. All right? So you will still need to rely on some reactive framework to gain this last factor of 2 that you need. But being light is not enough. It's mandatory, but it's not enough. It needs to be as efficient in terms of throughput. It needs to provide a simple programming model, and we are on track for that, because if we can build this model of thread, then the model in which you have one request per thread is valid again, you can use it. But it also needs to make debugging possible and to make profiling possible. We want all this. Okay? So this model of virtual threads that you have in 21 is actually doing that. And this is what I'm going to show you now. It's lighter by a factor of 1,000. You can literally have as many as you want in your application. And I'm going to show you how the stack traces and everything are working. And you will be able to compare with the rest. So how virtual threads are working? Well, the problem is that in computing, there is no such thing as a magical trick, right? There's no magical one. So virtual threads are still relying on platform threads. And you can't avoid that, because platform threads are the only way you have in your operating system to be able to run several things in parallel. So because that's the case, you cannot avoid using platform threads. All right. So at the core of it, there is a special fork join pool, which is a pool of platform threads. That the second fork join pool we have in the JVM. The first one was the common fork join pool that is used to run parallel streams. Okay, and the virtual thread is actually mounted on the platform thread from this fork join pool, and it has its own stack trace. It has its own everything, but it's still mounted on this stuff, so it's still running on top of a platform thread. All right? Now, there is a nifty stuff in it, which is every time you are issuing a blocking call in one of the JDK APIs, so for instance, you're issuing a network request, so you're using Java NIO and there is a blocking call there, then the API will check if it's running in a virtual thread or in a platform thread. And if it's running in a virtual thread, there is a special piece of code that will trigger that uses a hidden object in the JDK, which is called a continuation. And this continuation, as soon as this virtual thread is blocked, will actually move the stack trace of the virtual threads from the platform thread this is mounted on to the heap memory. So the stack of this thread is blocked, it is taken to the heap memory, and so it's not active anymore. And now this platform thread, this worker one, is available to run other virtual threads. And in a fork join pool, you have waitlists. Each thread has its own waitlist. So the next virtual thread that is in the waitlist will be taken and mounted on this platform thread so that it can run again. Okay? And at some point, because I did a network request that took probably 100 milliseconds, this continuation object I just talked to you about registers on the same operating system signal that will tell me, hey, the data is now available. Same operating system as my reactive framework. So when the data is available, my continuation knows it, and it will be able to put this stack that was in a heap memory back in my fork join pool. Now, it doesn't take it back directly on a worker thread. It actually takes it back in a waitlist of this virtual thread, of this platform thread, sorry. Okay? And in a fork join pool, there is this nice work stealing stuff that is being implemented, meaning that if this worker thread is busy and another one is not busy, then it will be able to steal this virtual thread and run it on some other worker thread. Okay? So that all these worker threads are kept busy through the lifespan of my application. So this movement of memory back and forth is really at the core of the performance of virtual threads. Okay? You block your code, there is an overhead to be paid, and this overhead is to move this piece of memory from the stack trace, from the stack of the platform thread, to the heap memory, back and forth. And if you think about it, it has two consequences. The first one is that all the garbage collectors now need to know where these virtual thread stacks are and need to check these stacks just to do their work, okay? To follow the references and to understand which objects are still live in your memory. So having this kind of thing implies to rewrite all the garbage collectors of the JVM, and there are several of them. That was part of the Loom project, okay? And the second thing is that if you have some native code that is running in this virtual thread, you don't want to do that. Because if you do it, in your native code, you can have addresses on the stack. If some of you have been doing some C or C++, you know that it's doable to have that. And if you have an address on the stack in your native code and you move your stack around, then you'll be in trouble because this stack is not going back to where it was, and the address you have on the stack is going to be corrupted. Okay? So this is what is called the pinning mechanism. If the virtual thread detects that there is a native call within the virtual thread stack, it will pin this virtual thread stack to your platform thread so that it cannot be moved. So that's one of the issues with virtual thread, the pinning stuff. So this solution makes it so that writing blocking code in a virtual thread is actually okay. It's not only okay, it is something that you should do. If you don't plan to write blocking code, then do not use virtual threads. It's useless. Use platform threads. Because there's an overhead in using virtual threads. Okay? Blocking a virtual thread does not block the underlying platform thread. Whatever you do in your virtual thread, you will never block the underlying platform thread. And this is exactly what you want. This is what you want in reactive programming. This is what you want everywhere. But the difference with reactive programming is that not blocking a platform thread in reactive programming is the responsibility of you as a developer. But when you're doing virtual thread, it's not your responsibility anymore. It's the responsibility of the APIs you're using. And these APIs are from the JDK, so hopefully they're working right. Okay? How is your platform thread used when you're dealing with virtual threads? Well, you have a virtual thread that is doing a first request to get the images, and then that gets the images and do something with them. So you launch your request, there is a blocking code, the virtual thread API detects the blocking code, takes your stack, put it on the heap, and your platform thread is freed. At some point in the future, your data will be made available, so this stack will be brought back to your platform thread to be executed again, and then we'll do something more, probably block again, and at some point will be moved to the heap memory and moved back to the platform thread. But in the meantime, another virtual thread will be mounted on this platform thread, block, will be moved to the stack, then moved back where the data is available. When block again, will be moved again to the heap memory, and then moved back again when the data is available. Okay? And in the meantime, it will be the same for another virtual thread. Move to the heap memory, move back, then move back again, moved again, and move back again. And another virtual thread, and another one, and another one. So virtual threads are also able to keep your platform thread busy 100% of the time, which is exactly what you want. What is the difference with the reactive model from the platform thread point of view? Can anyone see the difference? Yeah, there's no difference. There's no difference. From the platform thread point of view, there's no difference. So if you expect magically to have a 10x performance gain by using virtual thread, as long as your throughput is concerned, then you're in for a disappointment because it's not going to happen. If you have a good reactive framework, virtual thread will not bring you any better performance. Virtual threads are not about that. Virtual threads are about writing simple code, this kind of code, which is blocking code, instead of this not so nice, not to say ugly, patterns that you need to write to use your reactive framework. Okay? Virtual threads are going to handle the blocking API for you. So writing blocking code is okay, and this is what you should be doing. Do not think about running your parallel streams in virtual thread. That would be useless. That would actually degrade your performance. Okay? So what about we take a look at the stack traces. So this is a callable. Some services read images, always the same example. You run it in an executor service. This executor service does not pull anything. It's the new virtual thread per task executor. So it actually creates a virtual thread on demand every time you submit a task to it. And once your task is done, it lets this virtual thread die because there's no point in pulling virtual threads. Virtual threads are a lightweight resource, so you don't pull them. It's useless. Don't do that. Never do that. Just let them die and create more when you need them. Well, if you have something that goes wrong in read images, here is the stack trace that you have. So you have the first element, which is the execution exception, that takes you on line 81, which is where the get is issued. But if you check the stack trace of the cause, you have the exception in a read images line 12, but you also have the line 78, which is the place where your Lambda expression was issued. So now you know, you don't have to find, to grep or whatever, your source code anymore. Now you know where your Lambda was written and where your asynchronous task was launched. It's in the stack trace, which is such a relief. Do you like it? Yeah, I do. Definitely do. But what we had was not exactly this pattern of code. We had fetch images and fetch links. And you want these two tasks to be launched in parallel. So you could use this executor service pattern to do that, but there is a better pattern do it, which is the structured concurrency pattern. Structured concurrency is about creating an object, structured task scope, and you create it in a try with resources statement. This object is auto-closable. It's just like an executor service. It's going to create virtual threads on demand and let them die. And when you quit this try block, it will close this structured task scope and kill any kind of resource it still has. If you still have running virtual threads in it, they're going to be killed for you automatically. The pattern is the following. You just submit tasks to it. So it's a fork method instead of a submit method, but it works kind of the same. What you get is a subtask object instead of a future object, but it's almost the same, kind of the same. And then you call join. That's a blocking call. But if you're running in a virtual thread, blocking is OK. So that's perfect. And once you get that, you just call get, just as on a future object, to get your result. Okay? And when you exit the try with resources statement, everything is cleaned up. No more loose threads, as you had in the first example I showed you. Remember the loose thread you had? Here you can't have any loose threads because everything is closed and cleaned up. If one of the tasks, read image or read links, itself creates another structured task scope, which is perfectly possible, then closing the root task scope will also close all the others that have been spawned by the virtual threads. This is why it's called structured concurrency. Let us take a look at the stack trace. Suppose that something goes wrong in read images. Okay, so you have an exception there. It's line 62. And we are going to check the state of this subtask object because you can do that. And if it's in a fail state, it means that there was an exception that was thrown. You can get this exception by calling the exception method on the subtask object and print the stack trace. And it's directly the exception you need. It's not an exception that is wrapped in some execution exception. And this is the stack trace that you get. And once again, this stack trace take you on line 62. As you can see, let me go back to the code. And line 62 is where you actually passed the lambdas, where you forked your lambda. So you know exactly where you were when this read image was called, which is super nice. Okay. So with these two patterns, first, blocking a platform thread is not an issue anymore because it's handled by the API, by the virtual thread API directly for you. Second, you have stack traces that will take you exactly where your faulty code was called, which is much better if you want to debug your application. And by the way, also if you want to profile it, because now you have meaningful stack traces. And third, you cannot have any loose threads anymore. Why? Because you are using structured concurrency, and it's just like you had an executor service that you could close when you're done with it. And this can only be done because you are using virtual threads, right? You cannot do that using platform threads because platform threads are expensive to create, and so you don't want to let them die. You want to reuse them, obviously. So virtual threads are efficient. You have a simple programming model. It's just your good old imperative programming model with for loops, while loops, if statement, try catch, this kind of thing. The very classical blocking code that you've been referring to write for 10 years. Debuggability is as expected because in the stack trace that you have the point where your code, the faulty code was called, and the same for profiling. Now you still have one issue, which is thread local variables. Who is using thread local variables in your application? Not that many, I would say 10–15% of the audience. So it means that the rest of you are using thread local variables without knowing that you're using them. Because if you're using Spring Boot, you're using thread local variables. Okay? How many of you knows that there is a remove method on thread local variables? Yeah. Not as many as people who are using thread local variables. So thread local were created before the executor service pattern was introduced, like 4 years before. Okay? It means that when you create a thread local variables, the idea was, because this platform thread will die soon, everything will be cleaned up with the thread. But now that you are reusing your thread, if you do not remove your thread local variables and you put some kind of security secrets in your first request, it will be made available in the second request that has nothing to do with the first one. And that is called the security issue. What is wrong with thread local? Well, many things. Okay, probably one of the biggest one is that they may be kept alive forever. If you never remove them, it means that your thread will keep them forever as long as you reboot your application, which is, it's just as embarrassing as having loose threads, actually, having loose thread local variables. So the first thing is that if your application is using thread local variables and you plan to move to virtual threads, just by changing your executive service, for instance, that's one of the things you can do, it should work out of the box because thread local variables are supported by virtual threads. It's not great, but it is supported and it should work from a technical point of view. But there is a model which is meant to replace it, which is called a scope value. The pattern of code is super simple. A scope value is bound to the scope of a method call. And the method call is either a runnable or a callable, so it's actually lambda. Okay? So you create a scope value in that way, probably as a constant, public static final something, and then you can bind it when you call one of your runnable. So here, the scope value key will have the value key1 within the context of this do something smart method call. And outside of this context, the scope value is unbound. Okay? You can bound it several times, just like that, and to a different value. So this is how you use and bind scope values. Super simple. All right? And as you can see here, there's no concurrency. I'm not creating any thread, any platform thread, any virtual thread whatsoever. So it's independent of the fact that you're running in a given thread. How can you read it? Also super simple. You just have an isBound method to check if your scope values has been bound within this method call. And if that's the case, you just call get to get the value it has been bound to. Okay? It's immutable, but you can rebind it if you call further methods. So you can do that. Is it a good idea? I'm not so sure. Now, there is something to understand is that you don't want to have loose scope values. You can have loose thread local variables. You don't want to have loose scope values. So everything that can escape this method call will not see the binding of this scope value. What could escape this method call? Well, a thread could escape this method call. If you create a thread equal new thread, and you start it, then this thread will live past the return of this method call. Okay? And that's precisely the case where you do not want to pass this binding, because you don't want to have loose scope values. So if your method, let me go back a few slides. If your method call here create thread, whether they're platform thread or virtual threads, the code that is being executed in these threads will not see the binding. Binding is not transmitted. Okay? Because it would mean that this scope value would have an unbound binding, unbound in time, and you don't want that. Okay? But structured task scope are auto-closable. They have a bound lifetime within this method call. So all the virtual threads that are created within the context of the structured task scope will see the binding of your scope values. Okay? Let me go back here. If within my do something smart method, I create a structured task scope within a trial reversal statement, I know for a fact that when I exit this method, the close method of this structured task scope will have been called. Okay? And so no more virtual threads will be alive after this call to close. So all the binding of this close value will be done. Okay? So because this binding is bound in time, then it's okay for the API will transmit this scope value binding to the structured task scope. The idea is that you don't want to have loose scope values. You don't want to have loose threads. You don't want to have loose scope values. Everything is about controlling the lifespan of everything you create, which was not the case with the executor service pattern. So, in a nutshell, virtual thread and structured concurrency and scope values are about to fix issues with concurrent programming that have been there since the beginning of the Java platform. We talked about blocking code, so it's not an issue to block code anymore. We talked about debuggability. So now when you have stack traces in threads, in virtual threads, you have a meaningful stack trace that will take you where this virtual thread was created. And this is only possible because this virtual thread is created on demand, which was not the case with executor services, where you create your thread when your application is created. Okay? And you don't have any loose thread anymore because, and once again, this is because we have this new model of threads. When you're done with the virtual thread, you just let it die. Just kill it within the context of a structured task scope. And it doesn't give up on performance because it uses the platform thread, the underlying platform thread, exactly in the same way as reactive programming. So you should have the same performance with all these benefits: readability, debuggability, and no more loose threads or loose thread local variables. What are the plans currently for the JDK 23? Well, virtual threads were final in 21, so they will stay final. And I suspect that in 24 they will also be final in 21. So structured concurrency is still a preview feature. We don't know yet if it's going to be final in 24 and if there are modifications that are going to be made. There are things that are going to be to be changed when it comes to pinning. Maybe you've heard this issue of pinning in synchronized blocks. So this is currently being fixed. There's a first fix in 23 that you have, and the second fix that will take longer to set up, to develop, to write will be published later, but people are working on that. And scope value is also a preview feature as of now. Loom is great. Use it, check it, give feedback on the mailing list. Thank you for your attention.